In this follow along, we'll take a look at the Swern oxidation. This is a fantastic oxidizing system. One, because you'll notice that there's no metals used. So there's no heavy metals that we have to worry about for waste. And a lot of the byproducts are volatile. So we'll pay attention to that as we go through the system. We also have it fairly buffered. So although HCl is generated during the process, you'll notice that there's triethylamine used here as a weak base. It serves as both a buffer and as a base to do the actual E2 elimination that we need in order for the reaction to occur. So let's follow along. I've highlighted the different components of this reaction because it is a pretty lengthy mechanism, so that you can follow along and understand that what we're interested in is the alcohol. That's what we're trying to oxidize to get to and stop at the aldehyde. So this is an alternative to PCC, a less toxic, friendlier, easier system to work with. I will also mention that in PCC, getting rid of your chromate salts byproduct after the chromium's been reduced can actually be a little tough. It's very difficult to filter those away. And one of the nice things about Swern oxidation, as I mentioned, is that you're going to generate highly volatile byproducts that upon rotary evaporation will just go away. There's always a downside though. And one of those is that this one can be a pretty smelly reaction. What happens first? Well, the most common way to do these reactions is using oxalyl chloride, DMSO in excess, and some triethylamine. So the first thing we're going to do is activate the DMSO with oxalyl chloride. This is what oxalyl chloride looks like. And the DMSO dimethyl sulfoxide, we're going to draw it in its resonance hybrid where the O is minus and the sulfur is plus. This is a very common resonance hybrid for a sulfoxide. And we're going to do our 1,2 substitution. It's going to go in and up. Doesn't matter which carbonyl. You don't want to skip steps. And then we're going to come down and out. So now we have the oxalyl chloride unit is now bound to the DMSO unit. And we kicked off a chlorine. Now that chlorine is going to come back, and here's where a lot of stuff happens. The chlorine attacks the sulfur, and what you'll see is that there's a collapse. Right? We just formed carbon dioxide and carbon monoxide. Right, so we've got the sulfur with the chlorine on it and the dimethyl group, still positive, and we've made carbon dioxide gas and carbon monoxide, which is C minus triple bond to oxygen plus. So overall CO gas is neutral, but it does have formal charges. So CO2 is a gas, carbon monoxide is a gas. Poof, just goes away. Very, very volatile. What happens next? Well, now that we have this species, I mean, all of that is pre-treated. You add the oxalic chloride and the DMSO together. This all happens. And then you start slowly adding your alcohol. So in comes the alcohol that we're interested in. The alcohol reacts with the sulfur. And now we're going to lose HCl. Right? This hydrogen and this chlorine are going to leave. The medium is going to help with this. We're going to lose HCl. This gets us to here. I'm going to now draw in the methyl. I drew in because that hydrogen is actually really important. At this point, we've added the alcohol slowly into the solution using a syringe. We give that a little time, and then we add the triethylamine. And the triethylamine is going to deprotonate one of those hydrogens on the methyl. It's going to push the electrons into the carbon. And this is going to give us an ylide. Very similar to what we've seen in Wittig reactions. So this is kind of strange, right? We have a sulfur positive. Now we have a CH2 minus. There's our ylide. And then this is what's going to allow us to do the E2. So let me just draw this a little bit different. I'm going to angle it a little differently. This is always the key step in an oxidation. It's like an E2, but intramolecular E2, our base is actually the ylide. So it's intramolecularly grabbing the hydrogen. So here is our E2. The carbon minus grabs the hydrogen, makes the new pi bond, and gives the electrons to the sulfur. What does that give us? Well, importantly, it gives us our oxidized system. That was the product that we wanted to get. The byproduct is dimethyl sulfide. Smells like rotten eggs. Never in your life will you ever be so excited to smell rotten eggs, because once you start smelling rotten eggs, you know that your Swern oxidation is working. You have just generated the dimethyl sulfide gas, which again is volatile, makes your clothes stink, but yay, successful reaction, right? You can actually smell success from a Swern oxidation.